Lesson 84. In this lesson, we are going to explore another method for solving a particular kind of differential equations. Before we do that, I would like you to take a look at this can you solve question. Can you solve x squared dy by dx plus 2xy equals 1 using the method of separation of variables? Can you solve using a homogeneous differential equation method, meaning you can write everything in terms of a function of y over x and then you separate variables? Take a look. I hope your answer is no, because I don't think it's doable. So now, do we have another way to do this? Well, before we delve into the new method, take a closer look on the left side. Okay, pay attention to the left side of this equation. Does it look familiar to you? Like if I asked you to go back to, say, chapter 4, okay, when you first learn about derivatives, does it match up with a certain rule that you know? That rule involves having, something multiplied by a derivative in the first term, and then the original y multiplied to something else in the second term. Or what about the relationship between x squared and 2x? Isn't this the product rule? This function x squared times y. Okay, so what does this have to do with our next lesson? Well, let's take a look on the next page. In this lesson, we're going to explore the type of differential equation called exact differential equation, where one side of this equation takes on the form of the derivative of a product of two functions equaling to like v of x, just another function of x. Okay, and related to this method of solving exact differential equation is called an integrating factor method. We call any differential equation written in the form of dy by dx plus p of x times y equals to q of x a linear differential equation. And this one is first order because dy by dx is the first derivative. And the left side of this equation, we can actually brute force, use your creativity here, to transform it into an exact differential equation, like a product rule format, by introducing something called an integrating factor, I of x. So if I multiply I of x into the first term, I also have to multiply I of x to the other two terms, right, of what I started with the linear differential equation. If I must make this whole left side to resemble the product rule, so in simpler form, I times y prime plus I prime times y, then this I prime part is basically anything but y in the second term. So anything but y. So I can say that I can set I of x, or I prime of x instead, equal to I of x, p of x. So the bigger question here is, what is I of x? Is there a general form of this integrating factor that we can apply to any exact differential equations that can be solved using this method? Well, let's follow the steps here. So we're going to isolate p of x first. So that means I have I prime of x over I of x equal to p of x. Okay, then integrate both sides with respect to x. So integrate dx, integrate dx, and then this should allow us to find the integrating factor, because looking at the left side, I have 1 over I of x times I prime of x as the integrand, which implies that ln of I of x plus c would be the result. And on the right hand side, I can keep it as the integral of p of x dx. We're going to choose c equals 0 for simplicity. Which means that I of x, if I need to isolate that, remember c, we said this is basically 0, is then e to the power of the integral of p of x dx. And we can maybe use the box underneath to summarize what just happened, okay? So to use the integrating factor method to solve an exact differential equation, we have to make sure first we begin with a linear differential equation. And a linear differential equation has the first term as dy by dx and the second term as plus some function p of x multiplied by y equaling to another function. Once we recognize this format, then the integrating factor can be calculated using the formula. And this is found in your formula booklet, including the format of this linear differential equation, okay? And the integrating factor is I of x equals to e to the power of the integral of p of x, whatever that y is being multiplied to. Okay, so let me color code it here, maybe in green. So this p of x is this p of x here, okay? And then we can set that integration constant to 0, just to keep things simple. And then you can multiply both sides of the differential equation by this integrating factor to turn it into, you know, that product rule looking thingy. And then you can solve, okay, by integrating both sides to get a general solution. It sounds very complicated, but once you practice these steps, you'll become more sensitive to what type of differential equation you have at hand and which method you will need to use to solve them, okay? So let's take a look at example 1. Find a general solution in terms of y of the following differential equation. So let's analyze this particular differential equation. Does it look like a linear differential equation? Namely, the first term is dy by dx. That's good. The second term has y in it. That's good. Which implies that the p of x in our general, method is -4, right? The multiplier of y in the second term. Which means that our integrating factor I of x can be found by taking e to the power of the integral of -4 dx, which is e to the power of -4x. We're going to make use of this I of x, multiply e to the power of -4x to every single term in our differential equation. And then on the right side, e to the x times e to the -4x is e to the power of -3x. Okay? So why is this useful? Because when I examine the left side, it resembles the product rule of the function, so the derivative of the function e to the power of -4x, no change in the first term, multiplied by a function that is not changed in the second term, which is y. Okay? And my right side is still e to the power of -3x. I want y as a solution, which means that I should be taking the integral of both sides of the equation, which allows me to simplify the left side. The integral of a derivative is the function itself. And then on the right hand side, we have the integral e to the power of 3x negative multiplied by -1/3 plus c. So now we can isolate y by dividing both sides by e to the power of negative 4x. I have e to the power of negative 3x divided by e to the power of negative 4x. So you're adding 4 to negative 3. This is e to the x, okay? Plus c e positive 4x. And this is the general solution. Here is example 2. Find the particular solution to the linear differential equation x squared times dy by dx plus 2xy equals to 1. And it passes through the function that we're looking for, passes through 1 and 2. Okay. Well, how do we do this question? This is actually your think about it question here. Okay, so we'll go about solving it. But we have a problem here because the given function here does not begin with dy by dx in the first term. I have an extra x squared. So remember, in order to apply the integrating factor, we must keep our differential equation in the form of a linear differential equation. So first, let me put down some notes here. Write in the form dy by dx plus p of x y equals to q of x. And the good news is in your formula booklet, it actually prompts you by showing you this exact format of a differential equation before it indicates what the formula for the integrating factor is, okay? So make sure you cross-reference your formula booklet and be familiar with what's provided to you to give you hints. So what does it look like? That means I have to divide every term by x squared here. This means I have dy by dx plus 2y over x, right, equals to 1 over x squared. Next, we are ready to find the integrating factor I of x. The formula is e to the power of p of x, so whatever is multiplying y in the second term. So in this case, it's 2 over x dx. This is actually good news because 2 over x as an integral gives us e to ln x. And then I can say this is ln x squared, but I have e to the power of ln x squared, which is x squared. It actually cleans up a lot of things for us, okay? What's next? Right, you multiply this integrating factor of x squared now to every single term in your ODE. So x squared times 2y over x is 2xy equals x squared times 1 over x squared is 1. Good. Left side is the derivative of the function x squared times y, right? Remember, we're seeing it as a product rule, equals to 1. We're going to integrate. I'll keep it in blue. Integral dx. Okay, so here we know that we have x squared y equals to x plus c. I'm going to substitute the point now because in this question we are actually looking for a particular solution. So I'm going to sub 1 and 2. Okay, into the equation I have 1 squared times 2 equals to 1 plus c. C is equal to 2 minus 1 is 1. And so back to, let's call this star. It becomes x squared y equals to x plus 1. Solving for y, I have x plus 1 over x squared as the particular solution. Okay. If you're confident with this method of solving differential equations, you can actually try examples 3 and 4, which are basically the same idea. Okay, you just have to use your creativity to think a little bit about how you're going to prepare the format of the equation in order to solve it using the method of integrating factor. Okay, and then you can check part 2 of this lesson's video to look at the solutions.